Hi, my name is Niels, and as Jan already said, I'm a student and I work at Altair. And so I want to show you a little bit about Altair Activate today. Um, what are we going to talk about? I will give you a general instruction what Activate is and what you can do with it. Then we will talk a little bit why we are actually doing system simulation. Then I will show you two different model approaches. We will go a bit more deeply into that, and the different approaches how to model systems is something that we have a focus on today. Then I will show you the user interface layout of Activate. Then I will show you a little example in Activate of a lightweight car model. And then after this, we create a little model. I'm really looking forward to this. So general introduction. So what is Activate? Activate is software you can use to model and simulate continuous and discrete dynamical systems. And you can, of course, mix signal-based and physical-based modeling. Those are the two approaches I'm talking about, and we want to have a focus on this today. What's signal-based and what's physical modeling? Furthermore, you can do optimization, which is a very important thing for engineers because we always want to optimize our parameters of our models to a maximum or minimum. Activate also can handle Simulink models, which is also important for most of you because I think many of you already work with Simulink and you want to reuse your old models in Activate. So you just can import them and it works pretty good. Furthermore, you can perform co-simulations such as functional mockup interface. I think a few of you already heard about the FMI. It's a standard where you can exchange models from one simulation tool to another simulation tool and vice versa. There are two different kinds of FMIs. One is the model exchange, where just the model is converted to a package. And then there's also the co-simulation, where also the solver is also put in that package. So why system simulation? Why system simulation? Models are idealized images of real things and make it possible to better understand and optimize scenarios as well as making predictions. So that means, for example, if you want to develop a new car and you want to see how this car will behave in certain scenarios, you want to simulate it in different scenarios and you can make new predictions with it, change parameters. So that's the basic idea. Why are we doing this? Because real tests are expensive. Imagine you develop an aeroplane and at the first test, this aeroplane make a crash. So this is going to be very expensive. And also the second point, real tests can be dangerous. So I think this is going to be a serious situation for a pilot. And so we want to make predictions by using system simulation, how our systems will behave, and not just for the physical reasons, also for the economical reasons. We can weigh the cost and benefits of our idea that we try to develop. And if the simulation results are good and the system seems promising, this is also a part of the decision criteria if a system is going to be developed. So now we will talk about two different approaches how to create systems. This is not going to be a very detailed lecture about it, but it's pretty important today. So what you can see here is a table. On the left side, we have the signal flow in the table. On the right side, the physical modeling, or also called object-oriented modeling or component modeling. So The main difference is that signal flow-based modeling is causal, and physical modeling is acausal. I will go more into detail on the next slide. Inheritance is also a very important part of physical modeling because your models are made of several models, which are the same as classes, and they can inherit from other classes functions and functionalities. Multi-domain modeling is something that signal flow cannot do, but physical modeling can do multi-domain modeling. And there's one good point of signal flow modeling. You can see the equation of your model, which is very important for control engineers who want to set up controllers and want to know how their system behaves. So acausal and causal. On the right hand, you see a diagram of a signal flow-based model. And on the left hand, you see two acausal models. So let's take a look on the causal model on the right hand. Each block of this model is an explicit function depending on the input. The information flow of each block is depending on the input. That means the flow direction of information in this model is given. On the left hand, we look at the acausal model. Upper left, there's an electric circuit. And there you see there's obviously no direction, no direction given of information flow. Each of those components contains an implicit equation, and the flow of information is basically depending on the inner solution of each component. And this implicity makes it possible to set up those component-based models. So, for example, down here on the left down corner, you see a mechanical system, and you see a lot of clutches, and left and right of those clutches, there are flanges, and they are flanged on other components. So this is real physical modeling, very intuitive if you work a little bit with it, because you will set up the system like it's actually set it up in real life. So yeah, this is a bit, now we talk about inheritance, which is a pretty nice feature of model-based design with object-oriented languages. So imagine you have a class, a model 0, and you want to create a model 1. That's another model. And you can inherit the functionalities of model 0 in model 1. That's a pretty nice thing. On the right hand, you can see we even can, that's theory. I never did it on my own, but it should work too. You can inherit model 2 in model 3, but also have the functionalities of model 0 because model 2 was inherited by model 0. My favorite example for inheritance is the chess piece, because you have a pawn, you have, I don't know the English names, the horse and the tower, and each of those is a piece with the function a piece can move. And if you inherit this chess piece class to the tower, for example, all you need is to override the move function with the specialities of the tower, for example. So the next part in the table was multi-domain modeling. And this is something special for object-oriented modeling. We have different physical domains, such as electrical modeling, magnetic modeling, mechanics, and thermal, and even much more. There are a lot of free libraries for the Modelica language. Modelica is the language we are using in Activate. I will talk about this a few slides later. And you can actually mix up the physical domains. As you see here in the picture, you can see a little electric circuit. And of course, an electric circuit, a resistor gets warm. So there's some heat transmission to the environment around this resistor. Basically, what you see here is your computer. You have resistors in your computer, and your case is getting warm. So we have a thermal system and electrical system in one model. So yeah, Modelica is the most common language for modeling with object-oriented modeling. It's a free language. It appeared in 1997, the first time, the version 1.0. The last stable release is from 2017, and you can use it on basically every platform, Linux, Windows, Mac. Yeah, and this is what we are going to use in Activate. So let's take a short look at the user interface layout of Activate. Well, this is Activate. You can see here different browsers, and you can see a diagram area, and down below the diagram area, you can see the OML command window. The OML command window is basically a console where you can manipulate or change or make some processing on your data which have been generated by a simulation. And the palette browser on the right hand is, of course, where you get your blocks from. You can just select blocks, drag and drop them into the diagram area where you will do your modeling. On the left hand, also very important browser is the variable browser. This is where all your data which has been generated by the simulation will be stored and also will be accessible, and you can make it visible. Yeah, this is just a short slide to modeling. Of course, again, the palette browser, you can just drag it into the diagram area, setting up your models. And of course, which is very nice, we can mix up between signal flow and component-based modeling in one model, not in two models, in one model. We can here use signal flow-based components and object-oriented components. Like this lookup table is connected with this torque component where you can see the tau. So this is pretty nice. So, and if you want to, imagine you have a big model, a grown model with several functionalities. You want to create subsystems of those functionalities. And then you just click on it. On the diagram part, you want to merge to one superblock. And then you go to the menu bar and just click on this superblock button, and you will have such a nice superblock like you can see here. Okay, this is a very important part too. We want to define parameters for our model. So there's an button which is called Model in the menu bar again, and then you can open this initialization script. And this is like in most other simulation tools like Scilab and so on. You can just define your parameters, and the model will know those parameters. There's something you have to look for, something you should know about masking superblocks. A mask is something that you can create for your superblock, and where you can redefine variables and switch easily between variables to make your model more personalized, or how to say, more flexible in its usage. So you just go on Edit Mask, then you will have the mask editor. Then you see those objects in the dialog box. So, and there's just name parameter. Then you click on this button in the red rectangle, and this parameter creator will open. So what you type in now is you will have a parameter, and you will give it a name, a description. You can say if it's visible or not. Sometimes it's not necessary to make parameters visible within the mask. Sometimes yes, sometimes not. And the parameter is enabled, of course. And then you type in the value. The value is a parameter which you have written into the initialization script, like in the slide before. Because we have to reach through the value into the masked superblock, into this masked subsystem. This is very important if you mask a superblock. Well, post-processing, of course, is one of the most important things, because if we generated data, we want to visualize those data and maybe want to do calculations with those data. And therefore, for this, we have the so-called signal out block. The signal out block writes the structure into the variable browser. The structure consists of the time, a timeline, we could say, a time vector, or it's even a time matrix, and then of different channels. For example, if we have two connections to our signal out block, like we do have here in this example, we have two connections to our signal out block. We have a channel of 2. We have 2 channels. So this is how we do the post-processing and the visualization. Again, we go onto the menu bar, click on the model, and this time we just choose the finalization script. And as you can see here, we read the data from the variable browser by accessing the structure, the time, the channels, the columns and rows of the data we want to have, we would like to have. Then we just make plots like down here. We create a figure. We say, oh, this is figure 1 or figure 10. I always prefer to say figure 100, figure 101, 102, or if it's a totally another kind of figure, I prefer to say figure 200. It's just because I like the way how to call those figures. So yeah, how do we start the simulation, and what should we do before we start the simulation? Before we start the simulation, we should set our final time, which is the simulation time, the time of our system to be simulated. Like if we want to have 3000 seconds of time in our system, we will just put it in final time. Other options are also, we can choose from different solvers which suit to our system. We not take a closer look on this right now. And then we basically, obviously, we just start a simulation by click on this big button here with the play sign. So now I would just give you a little introduction to a lightweight car model. And I also want to show it to you within Activate. So I would just show you a few slides, talk a bit about it, and then I will show you the actual model. So this here is a part of the car model. a part I would like to show you, because you can see here different parts of the whole car, and we separated the parts into those subsystems. We merged the system parts into superblocks. So what is the main part of a car? Obviously, yeah, it's the driver, which is nothing but a PI controller here with two signals going out. The gas signal, well, that's a German word. Actually, it's called throttle or accelerator. Sorry for that. And the brake signal. Then we have our engine component, a gear, a differential gear. Then we have a right, a left wheel, and we have driving resistance superblock, which contains resistance like air drag, like drag resistance, for example, or if you have a slope driving up a hill, that's also resistance. We will take a look at this in a few seconds. So here we can see the driver subsystem. It's just a PI controller with anti-wind up. Yeah, this is actually how it looks inside such a superblock. As what you can see here is the driving resistance block, which in this example only contains some drag resistance, signal flow based. You can see the constant with the CW, and behind this you can see that function. This both components are signal flow based, and then connected to this force component, this arrow which shows to the right side. This is a Modelica component, which is basically just a force for a translational movement. And we just subtract the force of the actual moving force of the vehicle, the actual drive force of the vehicle. So this is how to combine these both approaches to model. Yeah, this is actually already what I showed you, how to define model parameters. A few words to the vehicle parameters at this point. Of course, you cannot just declare single parameters. You can also declare vectors, like we used for the talk table. There's the linspace command, which will, for example, make a vector with the lower value 0 and the upper value max torque engine. And 7 means we will have 7 steps between those both values. So we will have 7 values with a minimum and a maximum between those both values. The same for the brake force. Yeah, this slide, I know it's a lot of text, but this slide is actually just saying that if we change a parameter, we will see changes in our scopes, of course, in our plots. For in this example, we just changed the CW value, which is in English CD value, which is the drag coefficient, from 0.18 to 0.24. And we see there's in the plots a difference in the energy usage. So if we increase this drag coefficient, there's more energy used on the same distance, of course, because the resistance is much higher, or not much higher, but higher. So now I switch to Activate. And here you can see the actual lightweight car. Let's take a closer look what we have here. What you saw in the slides were just this part of the model. But of course, we also have the drive cycle, for example. Now I'm going to show what is a mask. You can see here, I made a double click on this superblock, and this is an actual mask. And here we can choose between a real drive cycle and an artificial drive cycle. So this is a pretty nice idea with the mask. We can go in here, and you see here a superblock for an artificial drive cycle and a real drive cycle. Both are deactivated, and the one will be activated we have chosen with this include diagram block. So we can have kind of, we can use a bit of logic. We can programmatically control our model. As you can see, the diagram choice here is diagram selection. So that means we can choose between this and this by changing our mask. And yeah, the drive cycle is just an output of our desired speed. Yeah, we want to have a certain speed, and our driver will just drive this speed. Will make the car drive the speed. I hope this at least. Let's see if it does. Yeah. Yeah, I will come to this why there was just this input mask right now. So right now the model is compiled, will be compiled, and sometimes this takes a bit more time, sometimes less, depending on how many programs you're using or what kind of drive cycle you're using. So this is what comes out. This is our results of the whole simulation. Now you can see the actual artificial drive cycle. I created some parts where it's faster or slower, and you can here see the energy as a function of distance. So I would just try click here again. Now you can see here we also can have a mask like this where you can redefine your parameters before simulating. And this is made if you go here in our initialization script. There's this input dialog function where you can create this mask and can make this possible to change those parameters right before the simulation. So yeah, we have also here we have a mask. We could just change the table. We could create another talk table. The talk table is a table where we have a function of the accelerator function, which is called guess, and of the torque. Accelerator above torque, or better, torque above accelerator. So this is how we can create mass. And now we go to the visualization part. You can see here, as I showed you in the slides, you have the signal out block. Go into post-processing, you can see here. Okay, so yeah, this is the actual model. So let's go back to where we have been. So now we will actually create our own model. Yeah, don't be afraid. It's not that bad as it looks like. I know there are some equations. So now I want to show you on a model how easy to use the object-oriented modeling approach is. And I want to compare directly with the signal flow-based modeling. So as you can see here, we have this car, and this car, the movement of the car is created by 4 forces: the brake force, the drive force, the drag force, and the rolling resistance force. We could see this as 4 components. This equation has 4 components. So yeah, 4 components. So we just start with the modeling. Look, the first is we have a driving force, a force that makes the car moving forward. So I just want to show you how fast this modeling flow is using signal flow based components and object-oriented components. Since there are 4 different components, we need, of course, the sum block with 4 inputs, of course. Because we have 4 forces, means 4 inputs for our vehicle dynamics, of course. I decided that we choose just a very simple model everyone can handle, because, yeah, it's just, I think easy models make fun and bring the feeling of success. So this is the first part. What we have here will be the drive torque, our first force. So then we have the brake force, which is this here. Since I know the names of all the blocks I use, or let's say mostly, I just searched for the names. You can also go into these Activate library here and look for your actual block you want to have, like drag in the gain, or look for multiplication, a product. This is the round product here. So we just connect this. Whoops. We can click this and click this, and there will be a connection made if we push the shift button on your keyboard. So let's take a look again. Divided by R. So R. And better. Let's do it the easy way. So this is the drive torque, and this is the brake force. So what can we do now? We can say we want to have a torque. Now I want to show you those both ideas in Modelica. So that's basically our torque. This is this component, and now we just need a brake, which is this simple component here. Can connect both. So you see we have more than, I think, 5 blocks here already, and we just need 2 blocks of Modelica here. So as you can see, if you know Modelica, you can model much faster and yeah, just faster and more intuitive. It's a very nice approach. So here we have the rolling friction. This is just a constant. I will declare the variables soon. Just give me a second. I already have, of course, also the finished model, if there will not be so much time left. But this is also very important, what I want to show you here. this is going to be the rolling resistance. The rolling resistance, which is a friction in Modelica. You see, this is a friction. But other than this component here, this is a translational movement and this is a rotational movement. So what do we need? We need a component that makes a rotational movement to a translational movement. So we look at mechanics, go to rotational, go to components, and look, what do we need? Okay, an ideal rolling wheel. So a wheel makes, obviously, a rotational movement to a translational movement. So now we have this and this. So this is our friction on the ground. This is the rolling resistance here. This is this. This will be this part of the components. So 4 forces, 1, 2, 3, 1, 2, and 3, and one more will be depending on the actual speed. We have a differential equation of second order. That means the first integration I always try to use German, but sometimes German is not working. Yeah, easy. Integral, not integration, it's integral. So yeah, this and this, we just make a flip, connect it here, connect it here. So this is how the model would look like without post-processing, without scopes in signal flow-based modeling. And this is almost how this model would look like in component-based modeling. This here is going to be beta signal. Beta is between 0 and 1, the brake signal. So what else do we need? We have the torque, which is this. We have the brake, which is this. We have a wheel, which makes from rotator to translator, and we have the friction. But now we also need a drag force. Modelica standard library doesn't have a drag force, but we can create a custom component within Activate using the Modelica custom component. Custom component. Yeah. Here we can name our flanges on the left and on the right for the Modelica component. I always like to give it the standard name flange A, flange A, flange B, which is standard in Modelica. Then we can add some parameters such as CV value, air density, for example, and yeah, I don't. It's just for presenting. I will show you the finished model right after this. So imagine this is going to be our drag force, and you can just put in here the Modelica code. I think this is for many of you the first time ever to see an actual Modelica code. I would just copy that from the already finished model, just for presentation. So this is here a Modelica code. This kind of code is in every Modelica component. You have your parameters, you have your connections, flange A, flange B, and then here's the actual equation. And here is the implicit equation of this component. So that's it, basically. That's it. And now we can say, oh, this is one super block here. This should not be like this. This should be not here. So this is one super block, and that's the other. So now we have a signal flow based model and a signal flow based model. So, but now I will show you the finished model with, because putting the parameters and do the post-processing and make the thing look good takes a bit of time. So this is the actual finished model here with a finished Modelica component with a mass. Of course, the mass is an important component too. A vehicle has a mass. So yeah, we have this and we have this. So both approaches have advantages and disadvantages. You obviously cannot see poles and zeros and the whole system theory in your Modelica component model, whereas you could see it as a very experienced engineer in your signal flow based model. So let's take a look and press simulate. And now we are compiling simulation. Oh, and plot on my other screen. So you can see it's exactly the same results with two different ideas of modeling. Yeah. What else could I show you? This is the whole post-processing I showed you already. So that's basically all from my side. I think it's time for questions, and I think I'm good in time, right?
Yeah, that's right. Thank you, Niels, for the introduction to the system modeling approach, both with signal and with physical modeling. So I think, yeah, it's really interesting that you can quite fastly set up like a physical mathematical model of your car, for example, or whatever system you are building, and have fast evaluations can determine different parameters, different forces, different effects, and how they will influence your model before going into full 2D or 3D modeling. So I think that's the idea behind it. And yeah, of course, we're open for questions. I didn't see any until now in the question tab, but of course, if you have questions, feel free and just type your question. So maybe while we're waiting, you mentioned also the possibility to build custom blocks and custom things in Activate. I think there are also, yeah, the possibility to couple other software to Activate. So maybe that will be an outlook that we can give. For example, from yesterday, we had the motion solve and its biomotion training.
Yes.
With the driver's chassis, and in most cases, a chassis will also require some sort of yeah, control mechanism or mechanisms and systems that will keep it stable, for example, or will keep it in lane. And for this, you can couple Activate to motion solve. So you can couple the system model to your chassis model and include motion solve in your Activate environment, which would then mean you perform some sort of co-simulation, right?
Correct. You can just put in this motion solve block and select your files and can integrate the whole motion solve model into your model. So far, I never did this on myself because I'm still a beginner in this field of motion solve, but yeah.
Yeah. So we have a question coming from Giant. Do people model non-linearities during model-based design in the design phase? Or build one first, then build prototype, and then based on that change the models? What's your experience? So I think the more non-linearities, the more complex your model gets, but I think that's one advantage in the whole model-based approach, that for non-linearities you don't need to really need a more complex model. You just need a different formula, right? So you just need a different block for non-linearity, or do I understand that?
Well, of course you can model non-linearities, sure. Usually most models are nonlinear, but for many times also models will be linearized to keep them more simple, and there will just be a small change of the actual results. This is my experience with non-linearities.
Yeah, I think it depends probably a bit on your application as well. So if you can linearize without too much loss of accuracy, that might make sense. But I think in model-based design, non-linearities are not that much of an issue as it would be with a full 3D model, right? So if I have a HyperWorks hypermesh composite model and I want to make it non-linear, that's a lot of effort because I need a lot of data, I need a lot of material, I need a lot of tests, I need a lot of basically feedback from real world back to my HyperWorks model to make it non-linear. While in system modeling, in the model-based system design, it's just a matter of what sort of equation do you enter, and you can directly edit the parameters of your nonlinear equation there. So that's it's probably less parameters that you would need compared to a 3D model.
Yeah, it's not a big problem with nonlinearities. For example, if you want to have, there is just a simple example in my mind, which I had in my studies, that we had a nonlinear system, which we wanted to control with a state-based controller, and we also had an observer, and we had this nonlinear system running at the same time with the linear system, and the linear system was the actual observer and the nonlinear system was the real system. So it's actually a goal of system simulation to also simulate nonlinear systems.
Okay. So another question not related to Activate. Will we, the webinar recordings? Yes, we will. We will post all the models and all the videos of today and yesterday on our website, on a server. So we will send you a mail after the webinar has ended, which will direct you to this SharePoint server, and you can download all videos and all the models to reproduce them at home. And you'll get that mail automatically after the meeting has ended. All right. Okay. So are there more questions on Activate? I hope you can use it. I think there's a lot of power behind it. There are so many use cases, not only from car design, but you can include a lot of things like electric engines, the control of your engine. You can do different studies and design. So that's really a very powerful tool, and hope you can use it. And as mentioned in the beginning, it is included in Altair. So if you have Altair license, no matter if the student or the sponsored license, you can use Activate, and it's in there. There are tutorials in there, and of course there are also a lot of demos in there. So Niels is just showing the demo browser, where you can just read in a few examples, try to reproduce them and understand them. All right, what are you showing there? A moon landing, or what is it? Simple moon landing?
Yeah, it's moon landing. You can control it with your keyboard, and you can try to make this kind of rectangle landing on the screen platform here. And this example is a pretty good example for the activations for discrete modeling with discrete times, as you see here, 0.1 as the period, sample period. So you have so many possibilities, not just making a simple car dynamics, of course.